Howdy! In this video we're going to go over example 6.1. It's on static failure theories. And the example reads as follows. A machine component is loaded so that the stresses at a critical location are sigma 1, 40 ksi, sigma 2, minus 30 ksi, and sigma 3 equal to 0. The material is ductile with a yield strength in tension and compression of 120 ksi. So what we have to do is we have to figure out what is the safety factor according to A, maximum normal stress theory, B, maximum shear stress theory, and C, maximum distortion energy theory. And then finally we're going to answer the question, which of the three theories would you expect to agree most closely with the actual test? So let me go ahead and swap screen so I can work on this example. Alrighty, so the first tip that I'll give you is whenever you're working with these examples, it's going to be to your advantage to go ahead and draw the Mohr circle for the stress state given. Now, when we look at this information given, notice that they give us the values of sigma 1, sigma 2, and sigma 3. Again, what that means is we're already working with the principal stresses. So again, just as a reminder, normally we would have just a problem. We would have to do statics and then solids with combined loading to figure out the stresses on a volume representative element. Then we would apply the stress transformation equations so that we get the principal stresses. And so that's kind of where we are right now. We're just starting with some principal stresses. And now we want to calculate, okay, what is going to be the safety factors based on the three different theories that we're covering here. So again, first thing you want to do is plot the principal stresses. Remember, the principal stresses are going to be the maximum normal stresses. When we look at the figure over here, when we notice this figure might or might not be provided in your homework problems. But if it is, we have to pay close attention. In this one here, we have just normals, right? Only arrows that are trying to stretch or compress this member. There is no shear stresses, right? So anytime you only see normal stresses, even if they don't tell you, that's already principal stresses. Alrighty, next one is, let's go ahead and plot them. So remember the plot, let me do it in blue. We plot on the x-axis the values for sigma, on the y-axis the value for tau. So let's start with the first one, which is a sigma 1 or principal stress 1 of 40. So let's go over here. This is the origin there. So we go 10, 20, 30, 40. And that's our first point. This is 40 and 0. Next, let's do the sigma 2. Remember, from this drawing, we can see that sigma 2 is compressing. That's negative. And in the problem statement is given as a negative value. So we have to plot minus 30. So minus 10, 20, 30 brings it over here. And this is point minus 30 and 0. This would be sigma 1. This is sigma 2. Then the last principal stress is the out of plane stress. They're telling us sigma 3 is 0. So that means that right here at the origin, sigma 3 equals 0. So let's go ahead and draw the Mohr circle for this one. Excuse me. So to draw the Mohr circle, right, there's a couple Mohr circles. Actually, there's 3 Mohr circles that we can draw, right, for the different planes, XY plane, XZ plane, and YZ plane. So let's draw the Mohr circle for this problem that we're working with, which is just between sigma 1 and sigma 2. These lie on a circle. Again, and we already have the principal stresses. So if we want to draw the circle, first we want to figure out what is the center of that circle. Well, we know that this distance here from the origin to sigma 1 is 40. And this distance here from the origin to principal stress 2 is minus 30, right? So the whole distance is 40 plus 30 or 70. If we divide that distance 70, which is the diameter, by 2, we're going to get 35, which is the radius. So let me go ahead and just write it down so I don't forget. The radius is 35, in this case, KSI. So why we need the radius? Because that's what we need to locate the center, right? If we start from principal stress 2, right, and I want to figure the radius, I need to add 35 to it. So negative 30 plus 35 is going to take me to 5, or roughly right here. If we start from sigma 1, which is 40, then we subtract the radius to get to the center. So 40 minus 35 is 5. So there we go. That's our center, which is at 5 and 0. And again, once we know the radius and the center of a circle, we can draw any circle, right? So I'm going to draw the radius going straight up over here. So it's going to be 10, 20, 30, and then 5. So there's a point right there. That's the radius. If I go down 10, 20, 30, 5, that's the radius line pointing straight down. Again, what is this point over here? This is at 5. X value, or your sigma, is 5, and the tau is 35. That's a point up on top. So now I can use this one to kind of go ahead and complete this big Mohr circle. Let me see how well I can draw this on the screen. Here we go. So from sigma 1, now I'm going to the positive tau, more or less something like this. Now curving down to sigma 2, and then from sigma 2 to the bottom point. There we go. So that's the Mohr circle. Here we go. Now remember, there's other 2 Mohr circles. There's one between sigma 1 and sigma 3. So between sigma 1 and sigma 3, I'll color that one red. And there's another one between sigma 2 and sigma 3. More or less like this. Why do I want to draw all of them? Because remember, remember the failure theories, right? The name tells you everything. Maximum normal means we need to look for the biggest normal stress, right? The principal stress is which one has the highest magnitude. For B, maximum shear stress, right? We want to find the absolute maximum shear stress. And so if you remember which one's the absolute maximum, right? We have 3 circles. We have the 3 circles, but the biggest shear stress is on the blue circle, right? And what is the value for the blue, right? It's going to be just the radius, which we said was 35 KSI. So that number we're going to use for the maximum shear. For the maximum normal stress theory, we're going to look at the normals, right? Which is 40, 0, and minus 30. And yes, for that one, we don't need to draw a Mohr circle, but it's always good to look at the whole thing because it's a real neat graphical way. If I look at this circle, immediately my eye looks at the biggest one. That's the plane that is seeing the largest stresses, right? And then in that plane, which is again from the blue circle, I can see that sigma 1, which is 40, has a bigger magnitude than minus 30. So that's the value I want to use. Now remember the formula for safety factor, which is the design overload divided by the normally expected load, right? So if I calculate for maximum normal stress theory, the safety factor is the overload divided by the expected, or what you're seeing. Well, what is the maximum, or what is the overload? That means that's the absolute value, right? This is going to be a number that comes from the material properties. When we're talking about the max normal, they want us looking at the yield strength of the material, because the stress can never exceed the yield strength. If it does, then we get into plastic deformation, or if it's brittle, it's going to break, right? So the maximum amount of stress that we can apply is 120 KSI. So this is this design overload. It cannot pass that point. And then what the maximum normal stress theory says is we're going to take the biggest principal stress, which is the highest normal stress, right? And if that stress is higher than the yield strength, then there's failure. So what that means for us is we're going to look at the circle, and we're going to look at the values for sigma and pick the biggest one. Well, the biggest one is sigma 1, which is a value of 40 KSI. And that's it. If we take 120 and divide by 40, we're going to get 3. So the safety factor, according to the maximum normal stress theory, is just 3. Next, the maximum shear stress theory. Again, the formula for the maximum shear stress theory, right, for the safety factor is the overload. So remember what the maximum shear stress theory says. It says that the absolute here we go again. It says that the absolute maximum in plane shear stress cannot exceed the shear strength of a material. Now, do you remember what the shear strength of the material is? Hopefully you remember. And if not, here we go. So here we have the yield strength of the material in tension, right? The shear yield strength. And shear is just the yield strength of the material divided by 2. Remember where that came from, right? If we have a little dog bone specimen and we're applying a little stress and we measure a strength at 45 degrees, we can do the math, and at 45 degrees, which is causing the shear, it's actually a value close to half of the yield strength that we measure. It's actually a little bit higher, but the approximation that we use is the yield strength divided by 2. So what that means is that the maximum value I can use is 120 KSI divided by 2, which is 60. And then what are we going to compare it with? We're going to compare it with the absolute maximum shear stress, right? That's the biggest shear stress on the biggest Mohr circle. So which one is that one? Well, if you answered this guy, you are correct. That's the biggest. Remember, we have 3. There's one in this plane, in the red one. There's one on the pink one, and the one on the blue circle is the biggest one. So the value of the tau, right, increases that direction. So this guy is the biggest one. So that one we calculated to be 35, which is the radius of the circle. So we divide by 35. So we plug that into the calculator. We take 60 divided by 35. This gives 1.71. So that's a safety factor according to the maximum shear stress theory. The last one is the maximum distortion energy theory. Remember what that theory says? For the maximum distortion stress theory, we would calculate an equivalent stress, sigma E. And then we compare it with the yield strength of the material. If the equivalent stress exceeds the yield strength of the material, then we got failure, right? So what is the formula for the equivalent stress? It depends on the data that's given. Sometimes we can get it from sigma x, sigma y, and tau xy. Or if we know the principal stresses, there's a couple formulas there. If you look at the equation and reference booklet, you can see that when the sigma 3 is 0, when the third principal stress is 0, then the equation for the equivalent stress is going to simplify to sigma 1 squared plus sigma 2 squared minus sigma 1 times sigma 2, and then the whole thing to the 1/2 or the square root. What that means for us, right, we can just substitute the values. So here we go. Sigma 1 was 40 KSI, so 40 squared plus sigma 2 is negative 30 squared, so negative 30 squared minus sigma 1 is 40 and sigma 2 is minus 30. And everything right to the 1/2 power. If we plug this into the calculator, hopefully I didn't make a mistake, I get that the equivalent stress is 60.83 KSI. And so now we can use that number into the safety factor equation to calculate the safety factor. So the safety factor is going to be the design overload, right? That one's from material properties. So again, with the maximum distortion energy, we're comparing always the equivalent stress to the yield strength of the material. So the maximum we can put is up to the yield strength of the material, 120 KSI. And we're going to divide by Let me put it symbolically. So just so that we put it here, is the yield strength of the material in tension divided by the equivalent stress. So this is 120 KSI divided by 60.83. This is a 60. Also KSI, units cancel. And when we plug that into a calculator, we get 1.97. Right? So we have safety factor for max normal at 3. Safety factor for maximum shear stress theory at 1.71, and safety factor for maximum distortion energy theory of 1.97. So the next question is, let me see if I can scroll. Yes. Which of the theory would you expect to agree most closely with the actual test or data? And this one here, basically all you have to do is remember from the PowerPoint that the best predictor, right? We have best predictor depending if the material is brittle. Where's my marker? Oh, come on. This thing froze. No. Again, if the material is brittle, we use the Mohr. And if the material is ductile, do you remember which one was it? It's the von Mises, which is another name for distortion, maximum distortion. So the best predictor for a ductile material will be the maximum distortion energy, this guy here. Hopefully you remember that they told us on the problem statement, the material is ductile. So again, because the material is ductile, we already know that the von Mises, or the maximum distortion energy theory, is the best predictor. So if somebody would ask you, okay, what is the safety factor for this application? Yes, we can calculate 3, right? We can calculate all this 3, but the best predictor is going to be this one over here. Why? Because the material is ductile, and that theory is best for ductile materials. So I want to remind you always to draw the Mohr circle. It's going to help you visualize the kind of the stress state for whatever problem it is that you're working with. And that's it. That's the biggest tip I have. Hopefully you found this example useful. If you found any mistakes or if you have any questions, do let me know in the comments down below. Otherwise, we'll see you on the next one.